Programming here is an old-fashioned term for optimization. So sometimes you find also semi-definite optimization. So I will use program and programming, and that refers to optimization problems. So what we're doing here in the Ringvorlesung is to get a glimpse of what nonlinear algebra might mean and how it is derived and built upon linear algebra. And today we're going to look at this from an optimization perspective. So, well, optimization in linear algebra, that's certainly linear programming or linear optimization. Now, linear programming, the objects we're dealing with are polyhedra, convex polyhedra, and we're optimizing linear functions over a convex polyhedron. And one way to define a convex polyhedron is to say we take the non-negative orthant in R to the n, so non-negative points in R to the n. We intersect this with an affine linear space, and in this way, say of dimension d, we typically get a d-dimensional polyhedron. If it's compact, it's called a polytope with at most n facets. So the question is, what should this be in the nonlinear context? Now, of course, we could write here nonlinear programming and nonlinear optimization, but we're going to give this more specificity today by taking a particular class of nonlinear convex optimization problems, namely semi-definite programming. So this is a fairly natural thing to put here. So the role of polyhedra is played by spectrahedra. And spectrahedra are strict generalizations of polyhedra. So spectrahedra, what we're going to do is we're going to replace the cone of non-negative vectors by the cone PSD, PSDN of positive semi-definite symmetric n by n matrices, and we're going to intersect that again by a affine linear space, and any such intersection is called a spectrahedron, and I will explain this. Well, let's first start with the name. Spectrahedron comes from the spectrum of a matrix that refers to the eigenvalues. So let's recall the spectral theorem from linear algebra. You have all eigenvalues, let me phrase it like this, all eigenvalues of a symmetric n by n matrix A with real entries, so symmetric matrices or quadratic forms, I noted by sim2 of Rn, and all the eigenvalues of such a matrix are real. And furthermore, the eigenvectors form an orthogonal basis. So this is clear. It's well defined if the eigenvalues are all distinct. If there are multiple eigenvalues, then in each eigenspace we can pick an orthogonal basis. That's the spectral theorem. Now furthermore, from this, we can derive the following fact. The following are equivalent for a symmetric real matrix. The following are equivalent well, all n eigenvalues are positive. Right? So we have our n by n matrix, the n real eigenvalues, but it might happen that they're all positive at the same time. And these are the eigenvalues of the matrix A, so are equivalent for a matrix A. Second condition, all 2 to the n principal minors of A are positive. So a principal minor is a subdeterminant, the determinant of a square submatrix, and principal means that the row indices equal the column indices. So I pick any subset of the rows, I then select the corresponding subset of the columns, I take the determinant of that square submatrix, and they're all positive. This includes the 0 by 0 minor, which is 1 by convention. Now here in this formulation, this is a rather wasteful formulation. So in fact, it suffices in this description to only take n of the principal minors in the first n. So the n by n, then the upper left n minus 1 by n minus 1, and so on. So for strict positivity, we don't need them all. We can get away with n. Now finally, the quadratic form is positive. So for every non-zero real vector, so every vector in Rn other than the zero vector satisfies that the quadratic form takes a strictly positive value on that vector. Now, whenever you see in the world of polynomials of nonlinear algebra, if you see a system of strict inequalities, and you would like to pass to the closure, as we would in solving optimization problems, then you're inclined to replace strict inequalities by weak inequalities. And in this case, this is legitimate. So I phrased this as theorem 2 in the notes. So again, also, I can here replace the word positive by non-negative. I can then also replace it here by non-negative, and it's still equivalent with positive replaced by non-negative. And here I can replace by greater or equal 0. So a matrix is called positive definite if the three equivalent conditions on the left-hand side are satisfied. A matrix is called positive semi-definite if the three conditions on the right-hand side are satisfied. Now, it's always good to practice basics of real algebraic geometry. So I like to make the remark that in general it is not true that you can construct a closure by making your inequalities weak. So here's an example. So is it always the case that the set where a polynomial f is greater or equal to 0, is this always equal to the closure of the set where the polynomial is strictly positive? So you would like to say that the values where a polynomial is strictly is non-negative is actually the closure. It certainly contains the closure, but in general it's bigger. So here's a simple example. I'm going to write this a little bit in a hidden format. X cubed plus x squared y plus xy squared minus y cubed minus x squared minus y squared. So this is a polynomial in two variables, x and y, of degree 2. Well, it turns out that this polynomial actually defines a half space. So you can factor this. So this defines the half space of all points that are strictly above the line where x plus y is equal to 2. So I've written this in a way that does not show the factorization, but in fact factors. But then if you take the second set, so this is the set down here. On the other hand, if you pass to the f greater equals 0, then you get the closure upstairs plus the origin. Right? So in this example, the f greater equals 0 defines a set that strictly contains the closure of f greater 0. Now this, you might think, does not concern you, but it does. It does actually come up here in the spectral theorem, because if you use the formulation of positive definite that uses very few principal minors, then this will fail. Okay? and I'd like you to think about this. If you get bored in the next 20 minutes, please think about it. So if you take the n principal minors that are at the beginning, the one that I aforementioned, and if you replace them by greater or equal 0, then the same phenomena will happen. So there are matrices that are not positive semi-definite, that have the first n principal minors non-negative, so it's exactly the same thing. But if we take enough principal minors, in particular if we take all principal minors, then we pass gracefully to the closure. Yes?
So can you fix this like in general if you pick enough polynomials that are positive and then you...
Yes,
then
you have, that's right. You can always... so can you always do that? Yes, the closure of a semi-algebraic set is a semi-algebraic set. Okay? I believe the closure of a basic open semi-algebraic set is not a basic closed semi-algebraic set. Remind you, basic means given by a conjunction of polynomial inequalities. So a basic open semi-algebraic set is a intersection of a finite list of sets like this. So an intersection of finite set like, that's a basic open semi-algebraic set. A finite intersection of things like this is a basic closed semi-algebraic set, I believe. So it comes, by Tarski's quantifier elimination, for example, that it's clear that the closure of a basic open semi-algebraic set is semi-algebraic, but I believe that in general it is not basic closed. Okay, but let's go back to the good world. So everything is okay for positive definite matrices if you take enough inequalities. So we have the basic closed semi-algebraic set, which I'll call PSD of n. The basic open let's call this the positive semi-definite matrices. Let's make it closed. So the basic semi-algebraic set of positive definite, semi-definite matrices. A, well, it is a closed convex cone of full dimension in the ambient space. Now, what's the ambient space? The ambient space is the space of symmetric n by n matrices. So that's an ambient space of dimension n plus 1 choose 2. So this has the full dimension n plus 1 choose 2. Well, it's closed, right, because we've chosen it to be closed. So semi-definite is given by these equivalent closed conditions. Now, why is it convex? Well, it's convex because it's defined as an intersection, infinite intersection of a list of half spaces. And to see this, think about this inequality from the point of view of A. So for fixed U, if U is a fixed vector, this is a linear inequality in A. This expression is linear in A. So what we're saying here is that a linear form is strictly positive in A. Here we're saying that a linear form in A is non-negative. So the third description describes our set PSD as a solution set to a list, an infinite list of weak linear inequalities, and that makes it a convex set. A convex set, by definition, is one that's given by a list of linear inequalities. I'm going to use this notation, this funny greater equal, to say that A is a positive semi-definite matrix. Okay, so again, our set PSD has several structures. It's a convex set, it's a semi-algebraic set, and it also has the spectral interpretation in terms of the eigenvalues. Okay, so now let me return formally to the definition of spectrahedra. So A spectrahedron is an intersection of this cone with a linear space. So spectrahedra are intersections of this cone. So S spectrahedron is this cone intersected with L, where L is a subspace of Sim 2Rn, the space of symmetric n by n matrices, and this is affine linear. So it's an affine linear subspace, by which I mean the solution set to an inhomogeneous linear system of equations in n plus 1 choose two unknowns, aij. Okay, so those are spectrahedra. Now, spectrahedra, just like polyhedra, have different representations. So here I've given you what's sometimes called the standard representation of a polyhedron. The standard representation says a polyhedron is the set of solutions, non-negative solutions to a linear system of equations. Okay, that's one way to specify a polyhedron. Sometimes you're more familiar with linear inequalities specifying polyhedra, but you can go back and forth between these, and this, like everything in life, requires a little bit of practice. So we have the same for spectrahedra. So we started with the equational representation. So the equational representation, well, let me write down the equations for a linear space, right? So the set of all X matrices, symmetric matrices of size n by n, that satisfy a system of S inhomogeneous linear system equations. And the way I'm going to write this is AI paired with X is equal to BI for I from 1 up to S. So here X is an unknown symmetric n by n matrix. AI is a fixed symmetric n by n matrix. And the inner product is the dot product, AI xi. So this is simply the dot product between the entries, but it's convenient to write this as the trace of the matrix product. So if you have two square matrices of the same size, then the inner product in the usual dot product sense can be computed by forming the matrix product and then taking the trace. That is to say, to add up the diagonal elements. And just to be super explicit, this is the sum over all I from j up to n, aij xij, and if you write this out for the symmetric matrix, this means that the off-diagonal entries sort of appear twice. So that's the trace inner product, and then this is the way to write a linear system of S inhomogeneous equations in an unknown matrix S. So that's the equational representation of a linear space, and hence of a spectrahedron, if we look at PSD solutions. Now this linear space, like every linear space, of course, can also be given a parametric representation. Let's look at that. So the parametric representation of an affine linear space is, well, you learn this in linear algebra, right? You have a particular solution and then any linear, and then a basis of the solution space. So let's do the same thing here. So there's any particular element A0 plus any linear combination of a basis. That's called the basis A1 up to AS. These are symmetric matrices, and the multipliers are just real numbers. Okay. So I have an equational representation of a linear space of codimension S. Here I have a parametric representation of a linear space of dimension S, assuming these matrices are linearly independent. Okay? This has dimension S, this has codimension S. Now in the second representation, our spectrahedron could be written like this. We could pull it back into R to the S, and that's the set of all x1 up to xs in the s-dimensional parameter space, such that the matrix represented by this parameter vector is positive semi-definite. Okay? Yes, question.
So those things, so the spectrahedra and the polyhedra as well, are usually lower dimensional, so they are not of
in this formulation, so this, if L is a, so let's take the second representation, so then L would be a linear space of dimension S, then typically this is an S-dimensional polyhedron having n facets, defined by n linear inequalities, okay? So for example, the way you should think about a quadrilateral in the plane, in the standard representation, this shape, this quadrilateral, naturally lives in a four-dimensional space. Namely, I take that four-dimensional space and I intersect a two-dimensional linear plane with the non-negative orthot. So in the standard representation of a quadrilateral, I take a two-dimensional plane and I intersect it with a non-negative orthot in R4. That makes these four coordinates x1, x2, x3, x4. Okay? That's the standard representation in linear programming, and here we're doing exactly the same. Okay, so this is our spectrahedron. So the engineers call this an LMI. So defined by an LMI. LMI stands for linear matrix inequality. So a linear matrix inequality is you have a symmetric matrix that depends linearly on some parameters, x1, x2, and so on. And an MI, a matrix inequality, just says the matrix is positive semi-definite. So an inequality for numbers is some number is positive or non-negative, and for matrices or operators, self-adjoint operators, it just says the matrix is positive semi-definite. And L, linear, because the matrix depends linearly on the parameters x1 up to xs. Now let's remark that polyhedra are special cases of spectrahedra. So proposition 3 says that every polyhedron is a spectrahedron. So this justifies this inclusion sign. This is indeed an exclusion, so spectrahedra generalize polyhedra. To be specific, polyhedra are those spectrahedra are the spectrahedra that arise when L consists of diagonal matrices. Right? So let's revisit this. So it could happen, right, that these matrices, A0, A1 up to AS, they might be just symmetric diagonal matrices. There's zero outside the main diagonal. Well then, this linear combination is a diagonal matrix. But this diagonal matrix is positive semi-definite. Well, a diagonal matrix is positive semi-definite if and only if the entries are non-negative, right? And that just says I have a system of n linear inequalities and s unknowns defining my polyhedron in the inequality sense. In the equational sense, up here, I would have, to get diagonal matrices, I have to include among the AI, I have to include the basis matrices that have exactly one, entry 1 outside the diagonal. So then, and then the corresponding thing here would be 0. So among these equations, I have to have the stipulation that the off-diagonal entries are 0. And then again, then I would recover the standard representation of a convex polyhedron. So if somebody ever asks you, what is a convex polyhedron? The answer, the correct answer is it's a spectrahedron of diagonal matrices. If somebody ever asks you, what is linear programming? People may not like this in Berlin. People ever ask you, what is linear programming? Linear programming is semi-definite programming for diagonal matrices. Or if a pure mathematician asks you the same question, what is linear programming? Linear programming is the abelian version of semi-definite programming. Matrices that multiply in an abelian fashion are diagonal matrices, and well, non-abelian are the ones that general matrices, right? Symmetric matrices multiply in a non-abelian way. Okay, now the logo of the nonlinear algebra group is one of these things. So let me first remark, so first example. Sometimes called samosa. So in the Nikolaistraße, on immediate vicinity, there are 5 Indian restaurants, and I assume that most of them offer samosas. So the samosa is a spectrahedron in n equals 3 dimensions. Actually, I should maybe write s equals 3 to be consistent with this notation up here. So S for spectrahedron or samosa. So this is the set of all x, y, z in 3-dimensional space, such that the matrix that has 1s on the diagonal and unknowns in the off-diagonal positions, that this matrix is positive semi-definite. Okay? So this is the samosa. Now you saw this on the first page in the very first lecture, and this was yellow. So in the first lecture I showed you the picture. This was yellow. The boundary I claim is a cubic surface. So why is that? Well, there's this spectrahedron. It consists of all matrices like this that are positive semi-definite. That means that the 3 eigenvalues are non-negative. Now, since closure behaves gracefully in this context, the interior of this yellow samosa consists of all matrices where all 3 eigenvalues are strictly positive. So if all 3 eigenvalues are positive, 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 then I'm in the yellow interior. I'm in the yellow boundary if exactly one of the eigenvalues becomes 0. So one of the eigenvalues is 0. Well, that means in particular that the determinant vanishes. The determinant is the product of the eigenvalues, and the determinant of this expression is a cubic surface. So if you evaluate this, you get a cubic polynomial, and that is the cubic surface. Now, as you saw in lecture 1, that cubic surface has 4 singular points, and at those singular points, there's 2 eigenvalues become 0, and only 1 is strictly positive. In any case, if you cross the yellow wall, then across on the other side at a typical point, you will have a matrix that again has, negative determinant. It will have 1 eigenvalue that's negative and 2 positive eigenvalues. At some point, you will run into the red elephant ears, also known as the Zariski closure of the yellow boundary. The red elephant ears are those points on the surface where you have 3 eigenvalues, 1 positive, 1 0, and 1 negative. That's the red stuff. As you go further out in your space travel beyond the elephant ears, then you will find matrices that have 2 negative eigenvalues and 1 positive eigenvalue. Okay, so the determinant of this matrix carves up x, y, z space according to the sign pattern of the eigenvalues. But most interesting one here is for the application is the stuff in the middle where the eigenvalues are positive or non-negative respectively to include the boundary. Okay, so we're speaking today about convex set. We're speaking about polyhedra such as this polytope, and we're speaking about spectrahedra such as this sponge. This is a spectrahedron. Polyhedra are special cases of spectrahedra. Let's remind ourselves one more time of these polyhedra, this polytope. So this is a three-dimensional polytope with 8 facets. The naive representation would be to write this as the solution set to 8 inequalities, linear inequalities in three-dimensional space. That is not the standard representation. If you take an optimization class, such as Math 170 in Berkeley, the first thing that we do in the undergraduate optimization class is take this naive representation and replace it by the so-called standard representation. The reason we're doing this is so we can run the simplex algorithm. In the standard representation, this polytope sits in 8-dimensional space, and it's given by a system of 5 inequalities. Oh, sorry, 6, sorry. Okay, the cube has 6 facets. I back off. So this has, I was already thinking ahead, of the octahedron. So this thing has 6 facets. So this polytope lives in 6-dimensional space. And it's given as the non-negative solutions of a system of 3 linear equations. That's called the standard representation of this cube. Now we're going to do, yes?
Now you mix it up somehow. So first you said inequalities and then...
Exactly. That was the point. We say this one more time. So there's an affine isomorphism, affine linear isomorphism between a full-dimensional object in 3-dimensional space called the 3 cube with a lower dimensional object in 6-dimensional space. The same 3 cube. They are the same. I'm just, changing coordinates. The first thing, let me call this the naive representation. The second thing is the standard representation. The first thing you learn in an undergraduate linear programming class is to write down the standard representation, because then you can embark on the simplex algorithm. Okay? They are the same polytope. Now let's do this for the spectrahedron. Okay? Now this spectrahedron might be the samosa or the sponge, so it's given by an LMI in 3 unknowns, x, y, and z. But equivalently, we can pass to the standard representation, which says that this is given by a 3x3 matrix, so it's given as a linear slice of the 6-dimensional, lucky same 6, the 6-dimensional cone of positive semi-definite 3x3 matrices. If this spectrahedron were, as we shall soon see, given by a 4x4 matrix, then it would be a linear slice of the 10-dimensional cone of positive semi-definite 4x4 matrices. Does this answer your question? Okay, so that's an identification that we make, but the identification is not so difficult once you've been through this in the case of linear programming. Yes, question?
So you have, in the higher dimensional space, you have equations.
That's correct.
Determining the same object as inequalities.
Absolutely correct. Absolutely correct. Okay, let's do one more example. Let's do a plane example. N is 2, or maybe S is 2, to be precise. Now let's do the equational representation. So L is a general plane, 2-dimensional plane in 6-dimensional space that intersects a general 2-plane that intersects the PSD cone, the 6-dimensional cone PSD of 3. Okay? So how should we draw the picture? Okay? So I claim the picture, and you see this in the notes, would look something like this. Okay? So the intersection itself is a convex set, and that convex set in the handout is, I believe, red. Okay, so there's a red curve that carves out a closed 2-dimensional convex set. Now, of course, I can pass to an LMI and represent this in a 2-dimensional plane. I can endow this 2-dimensional plane with a choice of coordinates, x and y, and then I have an LMI. Or I can just think about this in the standard representation. I have a linear system of 4 equations, and then this lives in 6 space. At any rate, the boundary of this thing is given by the vanishing of the 3 by 3 symmetric determinant. The 3 by 3 symmetric determinant is a cubic polynomial in 6 unknowns of degree 3 having 5 terms. Now if I take that cubic polynomial and I restrict it to the plane L, I get, a cubic in the plane. That plane cubic will be smooth, and we're going to call this an elliptic curve, a cubic curve in the plane. Now what is this other stuff? Let me maybe illustrate this by giving you a numerical example. So now let's choose coordinates, and let's write this in the other representation. So it's the set of all points x, y. Maybe the following matrix, x plus y. We go x plus y, 1, y, 1 is positive semi-definite. So this is the slice of the yellow samosa obtained by setting z to be equals x plus y. So I'm substituting z to be x plus y, thereby slicing the yellow samosa, and the intersection becomes red. Okay, now what's happening here? So the determinant, as I said, of this matrix, the 0 set, defines a smooth cubic curve. Now, somebody asked me, and rightly so, what are these other curves? Right? There are 3 other pieces that look like this, and they are black in the handout. Well, what I've drawn here again is the partition of the L plane, or the xy plane, according to the sign pattern of the eigenvalues of the matrix. Right? So inside here, all 3 eigenvalues of the matrix are strictly positive. On the boundary, one of them becomes 0. Then out here, well, so here in the red region, the eigenvalues are plus, plus, plus. Out here, they are plus, plus, minus. But as you traverse here, they become plus, minus, minus. So the yellow stuff here is part of the cubic curve. This is an irreducible cubic curve, x equals 0. So the yellow stuff, that is to say the black stuff in the handout, is the Zariski closure of the red boundary. Okay, so here on this yellow curve, I have plus 0 minus, the determinant vanishes as well. Now another thing that I drew in the handout was the dual curve. Let me make a few remarks about the dual curve. So duality, in this case, is between points and hyperplanes. Now this is quite natural if you follow a normal mathy version of a linear algebra class. The normal mathy version of a linear algebra class, there's a vector space and it's here. It has points, or vectors. Then there's a dual vector space, and it's over here. It has vectors. Now the vectors over here are linear forms on the vector space over there, and vice versa. Now a linear form here determines a hyperplane there. Okay? So points here are hyperplanes there. Points here are hyperplanes there. Now in an applied linear algebra class, the one that I subscribe to, often you identify the vector space and its dual by the choice of an inner product, and you draw them in the same picture. But let's draw them in a different picture. So here, if we pass to the dual, well, first of all, there is convex duality. So this red convex body up there has a dual convex body. So in the sense of convexity, this is the set of all points. Let's assume, just for the sake of a discussion, that there's an origin that's in the middle. So then this dual body is the set of all points, well, such that as a linear form, they dot to less or equal to 1 with every red point over here. That's the convex dual. Okay? Now on the boundary, a point on the boundary here corresponds to a linear form, a line that's tangent over there. So as you trace with your mouse, this is the first window on your screen, this is the second window on your screen. As you click here, as you click your mouse here, a tangent line appears up in the upper window. As you drag the mouse along the boundary, the tangent line travels around. Right? That's convex duality. But of course, this works in an algebraic geometric setting, so you can do the same over here. And, duality, of course, small things here become big there and vice versa, right? So therefore, the yellow exterior becomes a yellow interior in the dual. So the points here, now you click your mouse here, and then you get a yellow tangent line over there, right? Now you might wonder what happens at these singular points. Well, those are the asymptotes. These are the lines that are common. Tangent's a bad picture, so this one and this one has a common asymptote over there, okay? So that's the dual curve, and that such a dual curve always exists in algebraic geometry. So this is the set of all points, uv, such that the line it represents the set of all points such that ux plus vy equals 1 is tangent at the primal picture. Okay? Now, let's think a little bit more about this duality, and let's think about it from the point of view of solving the actual linear program, the semi-definite program. Okay? So semi-definite programming is the problem of optimizing a linear function on this closed red convex body up there. Okay? Let's take the linear function go north. Okay? Let's take the linear function, or let's make it a little bit, well, it's not a very good picture. How about, go north, northeast? Okay? So go towards Finland. Okay? So let's find the most Finnish point in the red convex body. Okay? Well, how should we do this? Well, first of all, this is a curve of degree 3. Let's suppose we solve this problem by calculus. Okay, so suppose the only math we know to solve an optimization problem is calculus. Now what we do is we write down the critical points of the objective function, and then we look among the critical points, the one we like best. So how do we do the critical points? Well, the objective function is go towards Finland, right? Go, and these are the lines. So let me say beep whenever I count a critical point. So beep, 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 beep. Okay? So there were 6 beeps. There was 2 yellow beeps, 2 red beeps, and 2 complex beeps that you didn't hear, right? There was the 2 complex conjugate beeps. So if you write this algebraically with the determinant of this matrix, there are 6 critical points. 2 of them we didn't like because they were complex and we didn't hear them. The yellow ones we don't like because they're not, in the feasible region. And then on the red one, there are 2 that we really like. That's the maximum, and the other one, that's the minimum, okay? Now what does this mean on the dual curve, right? What does this sweeping the finish line through, no pun intended, mean here in the dual curve? Well, it means the following, right? So here, the direction up here is some point down here, and this point, towards Finland, right? So now, what this means, the set of all lines, so this becomes a line in the dual plane, and this dual plane, we're going to say beep, right? Beep, 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 beep. Whenever I meet the dual curve, 6 beeps, 2 that you didn't hear, 2 inaudible, 2 red, 2 yellow. So this curve has degree 6. This curve has degree 3. Classical language, the degree of the dual is called the class. This curve has degree 3 and class 6. This has degree 6 and class 3. I might come back to this a little later, okay? Well, when we are solving an optimization problem, a convex optimization problem, and if we can draw the picture in particular, it's always good to think about duality. Okay, now let me formalize semi-definite programming. Semi-definite programming. Abbreviated SDP, means the following. Means optimizing a linear function over a spectrahedron. Now there are two versions. There's a primal problem and there's a dual problem. Just like in linear programming, there's a primal and there's a dual. Okay? Now let me write down the primal first. So the primal says minimize a linear function Cx, this is in matrix space, so this is the trace inner product between a cost matrix C and an unknown matrix X. Well, subject to the constraints, well, there are the constraints that this is in the PSD cone, and we have a linear system of equations, so AI paired with X should be BI, and let's say we have S constraints, I from 1 up to S. Okay, that's the primal formulation. So here I'm casting my spectrahedron in a standard form. So I'm taking the spectrahedron, it's a spectrahedron of codimension S, cut out in matrix space by these S linear equations, and up in matrix space I'm solving this optimization problem. In the dual formulation, the dual to this is in the other formulation. So min becomes max. So now I maximize the sum I from 1 up to S, bi xi, subject to C minus x1 a1 minus XS AS positive definite. So now I have the downstairs formulation where I have a dual problem in a space that's constrained in S-dimensional space with an LMI. Okay? This is the primal and the dual formulation of the same semi-definite optimization problem. Now, let's spend a little time understanding this. So I like to understand this duality. Now, let me first tell you what's bad about this. Okay? There are two things that I find really bad. Okay? Now, one thing I really find bad is the primal doesn't look like the dual. Right? They look different. Right? This has unknowns that the decision variable is this big X. Here the decision variable is the little x. Right? They look like very different. Okay? So first flaw, the primal and the dual look different. Now, second flaw, and I don't know which is more severe, this doesn't look like anything like the duality of plane curves. Right? That's beautiful and visual, and Italians do it in middle school. I mean, this is like really easy stuff, you know, nice duality of shapes in the plane. This doesn't look like anything like it, right? Because this is in a different spaces. This is in an S-dimensional space. This is in an n plus 1 choose 2-dimensional space. These are two shortcomings, right? So I have the primal and dual. Two problems are they look different, and they don't look like anything, you know, like the duality I've just drawn. Okay? Now, can I mitigate this? Well, maybe. Okay? But let's think back from linear programming. So back when we took Math 170, our undergraduate optimization class, we had the same problem in linear programming. See, after all, nonlinear algebra we're doing here to generalize linear algebra. So what was true in linear algebra? Well, in linear programming, we had the same thing. Right? In linear programming, the primal formulation is usually given in standard form, and the dual formulation is given in inequality form. Right? Same problem. Linear programming duality has the same flaw. Right? Now what about duality? The nice pictorial duality between a cube and an octahedron. The nice duality between an icosahedron and a dodecahedron. Same thing, we don't see them. Right? So in linear programming, so what I'm saying is that this formulation of semi-definite programming has two flaws, but linear programming has the same flaws. Right? Now, can that be fixed? Yes, the answer it can, but we won't do it here. That would go beyond, you know, what we're doing here today. I'm just going to hint, you know, but I'd like you to be aware that they look, and that makes the problem a little tricky, right? So there is a way of writing this symmetrically. There's a way to think about it in this form, but it's a little tricky, and you will have to talk to after today's lecture to figure this out. Okay, let's work with this formulation. What are we going to do with this formulation? Well, we can prove a weak duality theorem, and we can state a strong duality theorem. So let's do weak duality. So theorem. This is weak duality for semi-definite programming. So suppose little x is any feasible solution to the problem D, the dual problem, and capital X is any feasible solution to the primal problem. That's a hypothesis to P. Now somebody asked me, rightly so, what does feasible mean? Well, it's very good. Please, please, please send me questions. It's jargon, right? So I should have defined this. So feasible simply means that little x satisfies these constraints. So little x just says x is a vector, x1 up to xs, that satisfies the LMI. That's all it means to be feasible. And then big X is feasible, again, if x is positive semi-definite and satisfies these equations. That's a feasible solution. Could be very, very, very far from optimal. But if there are any two feasible solutions, then the objective function value of the feasible dual solution is bounded above by the objective function value of the primal solution. Okay? Now, this is nice, right? Because this is the thing you want to maximize, and this is the thing you want to minimize. Okay? Guess what's happening now? We're going to squeeze them together. Okay? So if equality holds, then clearly both are optimal. Where optimal solution means a feasible solution that actually solves the problem, right? So if you have a feasible solution that attains this minimum here, then we call it an optimal solution. And down here we have a feasible solution lowercase x that attains that maximum. We call it an optimal solution. Okay? Feasible, so a matrix X is primal feasible if it's positive semi-definite and satisfies this system of S equations. A vector little x is dual feasible if it satisfies this inequality, this matrix inequality. Okay?
So just a point in the spectrahedron.
It's just a point in the spectrahedron, exactly, just a point in the spectrahedron. Okay, let me prove this. This may be the only thing I'm proving today. Let me actually prove this. So I'm going to appeal to a fact. So the product, okay, so dot product or scalar product of two positive semi-definite matrices is positive definite, right? So I claim that if you have two matrices, both of which are positive semi-definite, then their trace inner product is non-negative. Okay? And that's a fact from linear algebra. You can prove this by diagonalizing one of them, right? So if one of them is a diagonal matrix, if it's positive definite, and the other one is any old positive definite matrix, well then the dot product is just a dot product of the stuff on the diagonals. That's a non-negative number. Okay? So the dot product of two positive semi-definite matrices is a non-negative number, and therefore 0 is less or equal C minus the sum I from 1 up to S xi ai that comes from the dual, and I'm pairing that with x. Okay, that's a non-negative number. So remember, this is now numerical values, this is a numerical matrix. They're both feasible, so therefore this is a positive definite n by n semi-definite n by n matrix. That's another positive semi-definite n by n matrix. Now the inner product is linear, so let's write this as C paired with x minus the sum I from 1 up to S xi and then ai paired with x. Well, what's that? Well, this one we just copy, right? So that's Cx. But this thing over here is Bi by definition, because capital X is primal feasible. This is equal to the sum I from 1 up to S, bi xi. Okay? And that's the end of the proof, right? This shows that this is a non-negative number. So something minus something else is a non-negative number, therefore something else is less or equal to something. Okay? So that proves the first statement. And the second statement is automatic, right? Because this holds for any feasible little x and any feasible big X. As soon as I have equality, that's it. Then they must be both optimal, right? Is that clear, right? Because if I have equality, well, if there were somebody who beats little x, some other x twiddle that walks in has a bigger value, well, then he's no longer bounded above by this guy. That's a contradiction, okay? As soon as you have equality, you're done. That's weak duality. So this justifies calling them primal and dual, okay? Remind you of the flaw, right? The flaw of this formulation, it doesn't look symmetric, it doesn't look pictorial. You can fix it, but I won't do it now. I'll do something else, okay? Now, the strong duality also holds, so well, let's get to this a little later. So let's do an example. I think it's good to see one example. Okay. In my example, S will be 1, so there's only one right-hand side, and then the corresponding B will be 1, that's B1 will be 1, and C will be the identity matrix. Okay, so let's look at this instance. Okay, so I look at the instance of the primal dual pair where S is 1 and C is the identity matrix, the n by n identity matrix, and B, the right-hand side, is the scalar 1. Okay, so then P is the following problem. It's to minimize the trace of X subject to A paired with X is equal to 1. Okay, now why is that? You just plug in. So the trace of X, well, C is the identity matrix, right? So the trace of identity times X is the trace of X. Okay, and then, there's only one equation, A dot X is 1. Right? So that's the primal formulation. Now what's the dual formulation? So dual formulation is maximize little x. It's a scalar. There's only one little x subject to the LMI that says take the identity matrix minus little x, A, positive semi-definite. Right? So this the primal and the dual. Okay? Now what does this mean? What does this mean? What's the optimal value? Now, we're going to get to strong duality, so in this case it's going to hold. So the optimal value will be the same. The minimum in the first problem will be equal to the maximum in the second problem. What is that number, right? Now that number, x star, is 1 over the maximal eigenvalue of A, right? You think about it for a moment, right? We're looking at this one, identity minus x times A. That's essentially, that's the characteristic polynomial. Among friends who like Moline series, right, the friends of Moline series, that's the characteristic polynomial. Rafaela likes Moline series, she'll tell us at 1:30. So that's the characteristic polynomial. Well, if you're looking for the largest x that said this is no longer positive definite, well, that's, the reciprocal of the largest eigenvalue. That's a definition of eigenvalue, right? The eigenvalues are the roots of this determinant. You take the determinant of this, the eigenvalues, or up to reciprocalization, those are the eigenvalues. So therefore, this is the optimal value. And the answer is, this is how you compute the largest eigenvalue of a matrix. Okay? Of A. So if somebody asks you to find the largest eigenvalue of a big symmetric matrix or complex Hermitian matrix, what you do is just maximize the trace over all solutions to the equation AX equal 1. Okay? That's equivalent. They are the same problem, right? Now, bear in mind, there are situations where you are interested in the largest eigenvalue, without knowing all other eigenvalues. There are many applications where you're interested in just the largest eigenvalue, and that's how you do it. That's one way to do it, okay? Okay, let's do a little bit more before we take the break. Let's at least fill...
In the first formulation, did you
Yes.
X to be what? Should be
Pardon
positive? Should we write it actually?
Yes, of course. That was subject to this one, and yes. And X positive definite, right? So, and this A, A is the, A is the A, okay, right? So here I'm cutting, the positive definite cone by one affine hyperplane, and then maximizing the trace over that intersection is equivalent to finding the largest eigenvalue of that matrix that does the cutting. Okay, let's go back to the general formulation. Here's an important lemma. Let me call this thing, which thing? Let me call this quantity star, okay? So this common quantity I'm going to call star. So if star is 0, well then we know we have an optimal pair. So if equality holds over there, if this is 0, then C minus I from 1 up to S, xi ai dot x is the 0 matrix. Okay, I will not prove this, but let me tell you what this means. So again, you have two positive semi-definite matrices. Okay? Now we know the inner product is a non-negative number, always. The only way that non-negative number can be 0 is if the product as a matrix is the 0 matrix. Okay, that's a very strong statement. If the number, if this star, if that number is 0, then this matrix as a matrix product is the 0 matrix. Okay? Now this might sound like shocking news at first, but it's not so bad once you think about diagonal matrices. So let's see what this means for diagonal matrices. So I have two positive semi-definite diagonal matrices. Now if the inner product is 0, then I claim their matrix product is 0. True, right? If you have two non-negative vectors whose dot product is 0, then their coordinate-wise product is the 0 vector. Who could disagree with that? Same in the non-abelian case of matrices. Okay? That's the lemma. Now this leads us to the so-called KKT equations. So these are the critical equations that I've just recently sung to you by beeping. Those are the beeping equations. So these are the Kuhn-Karush-Tucker critical equations that always hold. So for a primal dual pair. So let me write them down. So first of all, I have the linear equations coming from the primal, I from 1 up to S, and this. These are the KKT equations. So I have S linear equations, and I have n plus 1 choose 2 bilinear equations. These are quadratic equations. Okay, so here I have S equations that are linear. Here I have n plus 1 choose 2 equations that are not linear, but they are bilinear with respect to the unknowns. They're linear in the little x and linear in the big X. Okay, so it's a non-linear system of polynomial equations. Now, how many unknowns do I have? Well, same number, right? I have S little x unknowns, and n plus 1 choose 2 big X unknowns. This is a square system of polynomial equations. So square means same number of constraints as unknowns. A square system of S plus n choose 2 unknowns. So if today say in the afternoon, I ask you to solve a semi-definite program, what I'd like you to do is solve these equations. Okay? Of course, that's not how people do it in practice. Yes, question?
For the KKT system, I know that it is formed by primal feasibility, dual feasibility, and the slack condition. Where does dual feasibility or...
Okay, these are the equations. The KKT equations are the equational feasibility. The equations are satisfied. We're going to get to the inequalities in 1 second. So corollary 9 says, if we also have the inequalities, so the KKT conditions, they involve the KKT equations as well as the KKT inequalities. So if x is positive definite, and the LMI also holds. So the sum xc minus the sum xi ai is positive definite. If this also holds in this system, then we're good. Then we're golden, right? Then x is optimal for the primal. So big X is optimal for the primal, and little x is optimal for the dual. This follows from what we just discussed. So the KKT condition says that the square system of KKT almost linear polynomial equations is satisfied, and the two positive semi-definite conditions are also satisfied. We have such a solution, then we have a pair of optimal solutions. And today, and only if you're not called Daniel or Diego, if I say solve one of these problems, I mean apply this method, just for practice. Okay? Of course, this is by hand or by computer algebra. Now this comes by a name. So this amazing yellow condition on the upper right is called complementary slackness. So complementary slackness means that the product of these two matrices is the zero matrix. Okay? So you have two positive semi-definite matrices whose matrix product is equal to the zero matrix, then we call that, we're saying complementary slackness holds. Again, those of you who were fortunate to have taken undergraduate linear programming class know, of course, about complementary slackness for linear programming. So in linear programming, a pair of non-negative vectors satisfies complementary slackness if the entry-wise product is zero. So if you have two non-negative vectors, and then at any entry, the entry-wise, and the product is the zero number, then we say the two vectors satisfy complementary slackness. Right? And the same for matrices.
In your example, it's not the case, right?
It's absolutely the case in my example. Let's do it. Thanks for the question. This was not planned, but let's do it. So why is this satisfied? Let me first write down one thing, then we do an example, then we do the example, then we take the break. So complementary slackness implies, let me write this down, that the rank of the left matrix, I from 1 up to S, xi, ai, plus the rank of x is at most n. Let's contemplate this. Okay. So I claim if you have two matrices whose product is the zero matrix, then the sum of the ranks is at most the dimension of the space. That's the rank nullity theorem, right? So the rank nullity theorem says, right, so the kernel of one, whatever, right? So If the image of one matrix is in the kernel of the next matrix, then the image can't be too big relative to the rank of the other guy. So the sum of the ranks is at most the dimension of the space, okay? So complementary slackness gives us these rank containers. Okay, let's do the eigenvalue problem because Kaj asked for this. So I think that's what you asked. So let's do this in the eigenvalue story. So here, what does this say in the eigenvalue story? Okay. Let's say A is a general matrix. Okay, so A is a general matrix with distinct eigenvalues and all that. Okay. So what does complementary slackness say here? Well, so complementary slackness, let's just copy this. So we have the identity minus XA. That's a matrix. Times X is the zero matrix. So this n by n matrix times this n by n matrix is the zero matrix. Okay? Now, and little x is an optimal solution. Let's say we have a solution to this. Okay? Do you see the eigenvector? Does everybody see the eigenvector? Spot the eigenvector. Paul, do you see the eigenvector? Little x up to reciprocalization is the smallest or largest eigenvalue, right? Now what does this say? If this is the smallest eigenvalue, this matrix has rank n minus 1. This matrix has rank n minus 1, right? If A is a general matrix, I plug in an eigenvalue, it just drops by 1. It's rank n minus 1. It's an n by n matrix. What does this tell us about this matrix? Well, this matrix therefore has rank 1 at most. It's a rank 1 matrix because if I have two numbers, the first of which is n minus 1, and they add up to n at most, then the second number can be at most 1. Okay, so that's a rank 1 matrix by complementary slackness. Now, Paul, do you see the eigenvalue, the eigenvector? Yeah, a rank 1 symmetric matrix is pretty much the same thing as a vector, right? A rank 1 symmetric matrix is such a matrix. So this way, right? So rank 1 symmetric matrix is just the outer product of a vector with itself, right? So the column vector, it says up to scaling there's only one column vector, and that's the eigenvector. Okay, so the dual solution, which is the primal solution, is the eigenvector. Question?
Yeah, why did you say at most rank 1? Why did you say at most rank 1?
At most rank 1, because, where are we? So I have complementary slackness, blah, 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 blah. I have this matrix times that matrix is the zero matrix. But I'm saying the rank of this matrix plus the rank of this matrix is at most 1. Okay? If I have two numbers, the first of which is n minus 1, plus another non-negative integer, is at most n, that means the other number is 0 or 1. Okay? Very good. Which brings us to primary decomposition. This afternoon, of course, we're thinking about last week, we're thinking about the past, the present, but we always think about the future. Now, you may not have thought about primary decomposition being very, very useful for applications, and you may not have thought about primary decompositions being very useful for optimization, but here it is. This is all about primary decomposition, right? But what are we saying? We have a system of equations, right? Let's take the linear case. Okay, suppose we have two vectors, and complementary slackness holds, right? So this gives us a system of equations, right? This says x1, y1 is 0, x2, y2 is 0, up to xn, yn is 0, right? Is that clear? So we have an unknown vector, another unknown vector. We are trained in this class to think commutative algebra, right? We want to make a polynomial ring and 2n unknowns. Every equation, we write them down, they generate an ideal, right? So complementary slackness in the undergraduate linear algebra class gives us an ideal generated by x1, y1, x2, y2, x3, y3, x4, y4, and so on. That's a pretty simple ideal. It's an intersection of 2 to the n prime ideals. Because it's a radical ideal, every ideal is the intersection of radical is in the intersection of prime ideals, and those 2 to the n solutions are the combinatorial patterns for how it can be that two vectors obey complementary slackness. Same here. How can it be that the product of two symmetric matrices is the zero matrix. What are the combinatorial possibilities? I have no clue, but I can formulate this as a polynomial problem, and I'm learning again next week how to take an ideal, a radical ideal, intersect it, write it as an intersection of prime ideals. The combinatorial possibilities, well, how can it be that the sum of two non-negative integers is n? Well, it could be 0n, 1n minus 1, and so on. And that's primary decomposition. Let's take a 5-minute break. So exercise 3 is, how do you find the largest eigenvalue of any matrix in a given spectrahedron? See, the nice thing here is we just learned how to find, using semi-definite programming, the largest eigenvalue of a square matrix. Now, this may not be the best method, right? If you are Facebook, and oh gosh, I didn't say that. So if you are some company and you have a big, a million by million matrix, and for some reason you're interested in the largest eigenvalue, you're not going to use this method. You're going to do something else, okay? But the virtue of semi-definite programming is that you can answer these questions parametrically. If you have not one matrix, but you have a linear family of matrices, then you can answer that question parametrically in the linear family. So for example, you might have a spectrahedron, and you ask, among all matrices in that spectrahedron, what's the largest eigenvalue of any matrix, right? And then that's exactly a semi-definite program. So for example, in the samosa, right, among all yellow matrices in the samosa, what's the largest eigenvalue you see? Or in the samosa, let's say require that x plus 2y plus 7z is 12, right? Now that's a slice, right? That gives you an elliptic curve slice of the samosa. Among all matrices in that red slice, what's the largest eigenvalue you see? And then I think we should at least solve one of these optimization problems. So for example, we might look at the triplets spectrahedron. So again, I take a nice matrix like this with ones along the diagonal, but I'll give it a triplet structure, meaning it's constant along diagonals, x, y, z, like this. In figure 2 of the notes, there's a picture of the triplet spectrahedron. So the boundary is a quartic surface. The vanishing of this determinant is a surface of degree 4. That quartic surface, as you see in the picture, is reducible. It's the union of two quadratic surfaces. And let's just optimize, one function over this. So maybe 13x plus 17y plus 23z. Now, the nice thing about this example is you can still visualize the solution, right? You can look at the picture and ask for the northernmost point or the most Finnish point or whatever, the most Portuguese point if you're into soccer. And in any case, so let's do this. But the way I like you to do this systematically is to use complementary slackness. So the KKT conditions, so you write down the primal problem. Now this is the dual formulation. So you take this dual formulation, you write down the corresponding primal formulation, then you write down the KKT equations. It's going to be a system, a square system of 9 polynomials and 9 variables. They're not linear, but almost linear. You'll solve them, and then you look for, in the KKT equations, you also look for the KKT inequalities, and you pick the solution, and then you can look at where is it located.
All right, shouldn't be its matrix?
It must be an x.
X, yes.
Oh, there's an x. Oh, there's an x. Yes, typo. Yes, that's a triplets matrix. Yes. I want it to be triplets. X. Better? Okay. So the last half hour, I like to come to an application of all this called polynomial optimization. Now this got me interested in semi-definite programming. So the reason I got interested in semi-definite programming is because of this application. And as a sneak preview at the very end of today's lecture, we'll see how this ties in with the Nullstellensatz. There's a reason we talked about the real Nullstellensatz and about the amazing contributions that Professor Schmütgen has made to this. So polynomial optimization is we have a polynomial with real coefficient in n variables of even degree. So, I mean, this is an inhomogeneous polynomial of even degree 2p. And let me also, just for the sake of the discussion, assume that this attains a minimum value. So it's bounded below and it attains its minimum. You have to have even degree. If you have odd degree, right, then you don't attain a minimum, right? So for instance, one variable, so if n is 1 and p is 3, the picture might look like this, right? If p is 3, we have a polynomial of degree 6, and here is the minimum, okay? Now, how do you find that minimum? So the question is how to find. So I like to solve this problem. How to find f star, and of course you also want to find a point such that the value is attained. Right? So you want to find this point u star, and then the height is f star. Okay, so that's our problem. Okay, now in one variable, this is relatively easy. You learn this in high school, right? You take the derivative, but if you're in two or more variables, this becomes difficult. So we're going to approach this problem using semi-definite programming. But first, let's think about it this way, right? So this problem is equivalent to maximize lambda such that f of x minus lambda is non-negative for all x in Rn. Now that's equivalent to our problem. I mean, that's true for any unconstrained optimization problem, right? You want to minimize some function over r to the n. Well, that's equivalent to maximizing the best lower bound, right? So what does it mean to be a lower bound? A lower bound means if you subtract that value, you have a non-negative function. Okay, well, that's nothing. It's just a reformulation. Okay, so asking to minimize a function is equivalent to asking for the best, the largest lower bound. Okay. So now we're going to do a pass to a relaxation. Now relaxation, again, is jargon. Okay, let me define this. So relaxation means you're enlarging the feasible set. So somehow, you're changing the problem. So now it's no longer unconstrained, right? Because there's this constraint. So this constraint somehow defines a subset of r to the n plus 1. Right now I have n plus 1 unknowns. I have the x's and the lambda. And I have feasible pairs, but I'm going to enlarge the feasible set. And that's called relaxation. Okay, so you have a really hard optimization problem that's like squeezing you so tight, right? That's a very hard problem. Now I'm going to relax the problem. Now it's going to be easier. Now I can have lunch, okay? That's the relaxation. Same idea. You loosen the belt, okay? So that's relaxing. Relaxing, you're allowing more room, okay, for lunch. So maximize lambda such that the same thing, f minus lambda, is a sum of squares. Is a sum of squares of polynomials. Okay? Let's say it's a sum of squares of polynomials. And I'm going to abbreviate sum of squares by SOS. Okay? Now that's a relaxation. Well, is it a relaxation? So slowly. So now I'm requiring here. What am I saying? Maybe I said it the wrong way. Okay. So first of all, if it's a sum of squares, okay, so here I'm maximizing over a smaller set. Did I say it right? Please help me, Diego. So I'm actually, okay, so maybe I did it the wrong way. Maybe I did my demonstration the wrong way. So I'm maximizing over a smaller set. So I still, get a smaller value, and so this gives me a lower bound. Okay. Now, Suppose it were true that every non-negative polynomial is a sum of squares, then they are the same problem, right? So maybe it's true that every non-negative polynomial is a sum of squares, then this is the same problem. Well, that's not true, so we saw that that's not true. So we saw that the Motzkin polynomial shows that this is not the same. So here, in this relaxation, it's a truly different problem. So it could be that the value here is smaller. The optimal value is smaller. Okay? So instead of the first, we're going to look at the second problem. We're going to study the second problem. Now, when I first saw this, Diego's advisor, Pablo Parillo, showed this to me, many years ago. I thought that's ridiculous, right? I mean, here's a nice formulation. Anybody can understand. This is clear, right? Here I have clear, I go down, I do beep, I solve this problem, right? This seems like an easy problem. This is like a ridiculously hard problem, right? This seems like a much more complicated problem. That was my first reaction. Nothing could be further from the truth. So it turns out that this is the complicated problem and that's the easy problem. Okay? So when you first see this, your gut reaction is, this looks worse than that. You made things worse. But actually you made things better. Okay? That's the point of the next 20 minutes. Okay, so proposition 12. Actually, I will prove this. Let me prove this. So proposition 12 says, this relaxation is an SDP. Is a semi-definite program. Now I should make a comment that's sort of important that I haven't made yet. So a computer scientist giving the lecture, the very first thing I should have said, that SDP behave well, right? There's a polynomial time algorithm for semi-definite programming. So semi-definite programming, which is non-abelian linear programming, has an algorithm, the interior point algorithm, that runs in the same time complexity as for linear programming. And in practice, it's pretty good. It's okay. It's not perfect on large problems, but if you have a problem and you can reduce it to a semi-definite program, that you win, right? There's a polynomial time algorithm, and it's pretty good on small to medium-sized problems. Okay? So that's good. So let's prove this. I'm going to prove to you that the second formulation can be phrased as a semi-definite program. A little bit of notation. I'm going to write x bar upper p for the column vector of all monomials in n variables of degree at most p. Is that a question? Question? Okay. So x upper p is the column vector of all monomials of at most middle degree. Remember, I have this even degree thing, and I list all the monomials. Now G is an indeterminate symmetric matrix of that size. So it's an n plus p, choose n by n plus p, choose n symmetric matrix. This is called the Gram matrix. So if you're going to Google this is called the Gram matrix. Okay? It's a matrix of unknowns. So I have this column vector, and then I have a matrix of the same size, symmetric, with unknown entries. So now I'm going to write down a linear system of equations. So this Gram matrix will be the decision variable in the semi-definite program I'm going to formulate. Okay? So I'm now going to write down a system of linear equations in G, and then I'm going to require that G satisfy those linear equations and that it's positive definite, semi-definite, and that some objective function is satisfied. So I'm going to formulate a semi-definite program in the G space. So in the space of symmetric matrices of this size. Okay? So that's a fairly big matrix. So if P and N are big, this is a big matrix. Okay? So that makes semi-definite program difficult. So if N and P are really large, it gets difficult, but if N and P are sort of okay, then you can solve this. Okay? So the linear equations are, they require that f minus lambda is represented as this matrix. So x upper p times g, what was it, a column vector? So I should maybe take the transpose, right? And then I go x upper p. So this is a linear system of equations. Let's box this. So what are the unknowns? Well, the unknowns is lambda, right? And the unknown is g. And then this is a system of linear equations that takes place in the space of polynomials of degree 2p. Okay? The left thing is a polynomial of degree 2p, and there's just one unknown lambda floating around. Okay? The right thing is a polynomial of degree 2p, but there are lots of unknowns floating around, the entries of g, right? So this has degree p, it's a column vector. No, row vector now. This is a column vector. You multiply this out, you get some messy polynomial of degree p, and this equation means you collect coefficients and you set everything to be equal, right? So this is a linear system, an inhomogeneous linear system of equations in n, well, how many unknowns are there? Let's count, right? They're the entries of this matrix, right? So there are this many entries in G plus the lambda. Okay, there are this many, that's a big number. Okay, that's a linear system of equations in this many unknowns. Is that clear? So lots of linear equations. Now suppose there exists a solution. So suppose there exists a solution. So a solution is a pair of a g and a lambda such that g happens to be positive semi-definite. Let's suppose I can solve this a big linear system of equations and lots of unknowns. Let's suppose I can find a solution such that g is positive semi-definite. By exercise 2, a positive semi-definite matrix has a Cholesky factorization of the form H transpose H over the real numbers. Okay, sometimes called this, the official way, or sort of efficient way to do this is called Cholesky decomposition. Okay, but you can do this. So what I'm saying is, if you have a positive definite matrix, you can take the square root in the matrix sense. You can take a positive definite matrix, a positive semi-definite matrix, and factor it as some real matrix times its transpose. Okay? Just like numbers, right? So a number, real number, is non-negative if and only if it's a square of some other number. Same holds for matrices. Okay? And this is not hard to show, you know. Again, quickest way to see this is to diagonalize the matrix. So if your matrix is a diagonal matrix, well, then we're back to the statement about numbers. Right? So a diagonal positive semi-definite matrix is clearly the square, you know, has such an H, and it's true in this non-abelian case as well. So G has a Cholesky factorization, and this means that F minus lambda, the left-hand side, is equal to H times my row vector, a column vector transpose, that's a row vector, times HXP. Right? So that's clear, right? You just replace, you know, G to be H transpose H up here. And now you have X transpose HX, and you can write it like this. Now we're done, because this is a sum of squares. Right? I'm just saying that the left-hand side, I have written it as some vector dotted with itself. But what does it mean to dot a vector with itself? Well, the first entry you square it, plus the second entry you square it, and so on. Right? So this is a sum of squares representation of F minus lambda. So if you can find such a G, that's positive semi-definite, then you have found a sum of squares representation for f minus lambda, and hence a certificate for non-negativity. Now, R, let me write R for the number of rows of H is the number of squares. Right, so sometimes if you have a polynomial and you can write it as a sum of squares, you'd like to use few squares as possible, and the number of squares you need is the rank of G, right? You can arrange it so that H is a rectangular matrix with a few rows. Okay. So we're almost done, right? So every SOS representation has this form. So you have to argue that the converse holds as well, right? So if f minus lambda is a sum of squares, then you interpret the sum of squares as the dot product of a vector with itself. Now that vector has entries that are polynomials of middle degree p, right? But of course a polynomial of degree p is, well, it's a row vector times this column vector xp. That's clear, right? So a polynomial of degree p is this column vector on the right and some row vector on the left. A bunch of polynomials of degree p is a matrix times this thing, okay? So this works both ways, right? So if you have a sum of squares decomposition, that means you're writing this f minus lambda as the dot product of something with itself, and something is a vector, each entry of which is a polynomial of degree p, and therefore there's a corresponding matrix H that writes these polynomials in the basis.
Sorry, is it obvious that every sum of squares can be written as sum of squares of at most that many?
Yes. So the question is, so why can I bound the degree?
Yes.
Okay. So suppose I have a polynomial of degree 6, and I have a sum of squares representation. Suppose in this sum of squares representation, somewhere I have, a polynomial of degree 4. Well, then the square of it has has degree 8. Now, but maybe I can cancel, right? Maybe this, as I take the sum, I cancel and get degree 6. Well, that cannot happen because I have polynomials. Because I have positive numbers. So if I have a sum of squares of polynomials, let me say this again. Suppose I have a bunch of polynomials and I take the sum of squares, okay? And let's say the largest degree of this polynomial that I see somewhere is 7, right? Then each square, so then the squares have degree at most 14. Then I add up the squares, the result has degree 14.
No, sorry, it was not my question.
No, that wasn't your question.
My question was, if f minus lambda is a sum of squares.
Yes.
And why can I
Find H.
Yes, find H, because it might happen that it has
Okay.
more sum of squares.
Okay, so if f minus lambda is a sum of squares, so let me write this down. I tried to say this, but I didn't say it very well. So if f minus lambda is a sum of squares, so I from 1 up to something r gi of x squared, okay? So each gi is a polynomial of degree at most p. You agree?
Yes.
Okay. So therefore, each gi is equal to a vector. Let me call it, or g is bad. Huh? How about p for polynomial? Okay. So then I'm going to take a row vector, big P, times x. Oh, p is really bad. Huh? We used this already. Huh? How about ui? Okay. Let's do something sneaky. Let's do something that has a Greek analog. So how about di, okay? And then I make a vector delta. So delta is a row vector, right? So every polynomial di of degree p is the dot product of a constant row vector delta and the column vector x upper p. Okay, so very good. So this means this is the sum I from 1 up to r, delta I, the row vector, x upper p squared. Okay? Okay, now that's the dot product, right, of something with itself. So So now I simply take delta I and I make it the row of some matrix H. And I get this.
Yes. But why R is smaller than
Oh, why R is
plus,
the...
n plus p choose n?
I'm sorry?
The lemma. I mean, you can each.
Ah,
You
okay.
can cancel something.
Okay, so this is like not.
Maybe I didn't understand the question.
So why
Sorry.
R is not greater than n plus p choose n?
N plus P choose N.
So because you want to have H to be.
Why is R less than less or equal to the dimension?
Oh, I see. Okay, so the question is in the Koleski, so I have this matrix, okay. So I claim, so this matrix has some rank. Okay? Now the rank is at most n. So among matrices, an n by n matrix has rank at most n. Okay? So that rank R is at most n. So I claim you can factor this as H times H transpose, where the number of columns is the rank. And that's at most n. Okay. Okay. Okay, so now, let's first of all, what does the SDP want to solve? So SDP we want to solve, so we maximize lambda subject to the red equation over there, subject to this red equation, system of equations, and G positive semi-definite. Okay, so that's the problem we want to solve. We want to like lambda, I want to maximize lambda over all solutions to the red linear equations, and G is positive semi-definite. So now how do you do this in practice? Well, we're going to do it. Okay, so exercise 8, use this to actually minimize a polynomial. Minimize x to the 6th plus 5x cubed plus 7x squared plus x over all real numbers. Okay, so you have this optimization problem, and you forgot calculus. You forgot how to take the derivative of this polynomial. You do not remember that the derivative of x to the 6th is 6x to the 5th. We do not remember that. So therefore, we will write this as a semi-definite program. We say, let's find the largest lambda such that this thing minus lambda is non-negative on the real line. Now that's equivalent to saying that this minus lambda is a sum of squares of cubics. And you do exactly that. You write f minus lambda, and this is the column vector of length 4, whose entries are 1, x squared and x cubed. Question?
Is it equivalent or is it the relaxation?
In this case, it's equivalent. So polynomials in one variable that are non-negative are actually sum of squares. Okay? And so now you have an unknown 4x4 matrix with 10 unknown entries. G is lambda is an unknown, so we have 11 unknowns here, and we're going to solve it. Okay? So today at 2:15 p.m., one of us, one of you, well, we'll start at 1:30 with invariant theory. So we start with the past, invariant theory, then we move on to the present, semi-definite programming, and time permitting, the future, which is primary decomposition.
Why actually this relaxation works? I mean, in general, there are much more.
Why does the relaxation work? Okay, okay. First of all, how do you do this? So hint. So in example 13 in the notes, it's done explicitly for a quartic. So to solve this problem, you read example 13 and then you apply it here. Okay, so Kash has a very good question. Why does this actually work? Let me say a few general remarks. So general polynomial, and then we'll discuss, does this actually work? Optimization with constraints. Okay? So I claim this works. Take my word, for the next 3 minutes, believe me. Okay? So then I'm going to justify it. So I claim this is a very good method. Well, here I talked about minimizing one unconstrained polynomial of r to the n, but in applied problems you have tons and tons of constraints. So what about a big polynomial optimization problem with many constraints? Well, you can always get a semi-definite relaxation from an earlier lecture, from the Positivstellensatz. With degree bounds. Right? The Positivstellensatz gives you a syntactic description of non-negativity. If you have a semi-algebraic set, such as this bottle, which is given by polynomial inequalities of various sorts, and you want to minimize some function, like go north on this bottle, right? Then you can do exactly the same thing. Then you can write the certificate. So you want to what do we want to minimize? Let's say you want to minimize some function, right? Then you can say that this function minus lambda should be non-negative on the bottle. But that condition that f minus lambda is non-negative means that f minus lambda being positive has no solution. F minus lambda greater 0 has no solution. We have a certificate. So f minus lambda has no solution if f minus lambda is some crazy thing involving sums of squares. Right? That's the Positivstellensatz. Now suppose this Positivstellensatz certificate had bounded degree, has degree at most 10. Well, then you write it down. It involves sums of squares everywhere. So every ingredient is a semi-definite program like this. That's it. So that's the standard way. A standard way nowadays, very often, you talk to people in engineering. When you say the word polynomial optimization or convex polynomial optimization, that's what they mean. Okay? Now this is sometimes called the Lasserre hierarchy. So Lasserre hierarchy, especially in computer science, this is often called the Lasserre hierarchy. And hierarchy because you can up the degree. We do not know a priori good degree bounds, but let's try it, right? We start first with, let's say there is an Nullstellensatz certificate in degree 4. Maybe we succeed, then Kash is unhappy. Then we go to degree 6, still unhappy. We go to degree 8, right? That's called the hierarchy. You go up and up and up in degree. So Lasserre is one name that's often affiliated with this. The other one is Parillo, Pablo Parillo. So he will be here in the second week of August. There's a school here on numerical methods and algebraic geometry, and that will be one of the 3 themes. Is polynomial optimization. If you have a optimization problem involving polynomial equations and inequalities, you can always do this. And we're going to learn how to do this. But I think before learning how to do this, let's first practice how to minimize one polynomial in one variable of degree 6. So today at 2:15, we're going to do this one. Now, why does this work? Now, that's a very good question. Now, if it were true that every non-negative polynomial is a sum of squares, then it would work. Now, maybe most polynomials that are non-negative are sums of squares. Well, we don't know, right? There are some results that say no, most are not, right? And in fact, often the Nullstellensatz is sort of hard. But in realistic, so we do not completely understand that, but in realistic scenarios, it actually works. In fact, there's a project right now done by Anna and Diego and Lynn, who's somewhere over there. They are so desperately hoping that it fails, right? The whole point of their project is they have some problem in 13 dimensions, and all they look is one example where it fails, right? It always works, but they're looking for an example where it fails. They would love to find, in their instance, one example where it fails.
You mean when
where the semi-definite relaxation does not give the correct answer, exactly. Anyway, so that's a big discussion. There's a lot of research about this. We have only minus 1 minute left, so I thank for your attention. I'll see you at 1:30.